In this video, we're going to look at some of the perils of using pseudo-random generated variates, and in particular some problems that can arise with a linear congruential generator. Now, in the script I've put up here, you can see that I've taken the LCG generator that we developed in a previous video, which is this bit of code here, where I generate a set of variables, a set of variates, which I put into the array LCG vals. So as you can see, I've used a linear congruential generator here. I have the initial seed over here, and I generate the successive values according to the LCG formula here. Now you can see at the top I've defined that I'm generating 15,000 samples, and I've also defined another variable n, which will be the samples I'm using for my Monte Carlo estimate, and you'll see that it's 1/3 as the size. Why is that? Well, if we think about in the previous video how we calculated pi by sampling values within a circle, we can do the same trick in 3 dimensions. And so in this part of the code, I estimate pi. I have the tally for the accepted values and the rejected values as before. And I now sample over 5,000 samples. So for each sample, I generate an x, a y, and a z value, which I do here. And you can see that I previously generate the array LCG values, and I simply read out the values that I've previously obtained. And by using this syntax, I can pick, for the first x, y, z triple, I can pick the first element, the second element, and the third element of the array, and so on for the other points, which of course is why n samples, the number of random variates, has to be 3 times the number of Monte Carlo samples that I'm taking. So I do the same procedure as I had before. I calculate whether or not that generated point lies within r equals 1, and if it does, I accept that point, so I add 1 to the tally. So this line here, line 37, is the calculation of pi. And this differs from the 2-dimensional case because in 3 dimensions, the upper right quadrant is 1/8 of 4/3 pi r cubed. Remember that r equals 1, so that we are estimating pi over 6. So if I add up from those 5,000 samples and I calculate the number of accepted variates that lie within the sphere, and I divide that by the total number of samples, that is an estimate of pi divided by 6. So my estimate of pi is simply 6 times that, and then I can display it. The rest of the code here is simply generating color-coded points. So I generate a set of accepted points in x, y, z, and the corresponding array of rejected points, and that's just so I can plot them. So I can plot them in 3 dimensions using the plot3 command afterwards, and I can just run this now. So if I run this, you can see that I generate pi, and I generate a sphere of points, which seems great. So you can see I can rotate this, and I see that I'm generating a sphere of points. What I'll do now is I will comment out the part of the code that plots the points which are rejected, because I'd like to have a clearer view of just the red points. So I'll run that again, and I can see that quite clearly, and everything looks fine. And I estimate a value of pi at the bottom, which is as I would expect. Now let's look at what can go wrong if I change the parameters of my random number generator. Now, I'll leave this to you to check that this problem does not arise in 2 dimensions, but it does arise in 3 dimensions. So let's change this parameter a here, and I'm going to change that to 2 to the 16 plus 3. Well, why would I do that? Well, this collection of a, c, and m happens to be a well-known set of LCG parameters that was used widely in compilers in the past. So some random number generators, in particularly old code, may even have numbers like this. Now watch what happens when I run the code one more time. Oh dear. So you can see that with this selection of parameters, that when I rotate the samples, you'll see that they lie in planes. And this occurs whenever I generate triples or higher numbers of coordinates, if I were to do a 4-dimensional integral, for example, or a 5-dimensional integral, rather than this 3-dimensional one, then I would also see this problem. It doesn't arise in 2 dimensions. So you can see that in certain orientations, the numbers still look randomly distributed, as I would hope they would be. But for certain values of these parameters a, c, and m, it appears that the random variates are insufficiently mixed. They're insufficiently shuffled. I need a shuffling action on top of this, this calculation here in order to get the right behavior of the random variates. And it's also to do with the fact, the way in which I have generated pooled numbers from the pile, as it were. So if I had a set of variates, LCG vals, by picking them in successive triples, this is the reason why I'm getting this problem. There is another way that I might have picked these numbers out. Let's see how else I might have done it. I might have done it by selecting the value I. So all the values, all the x values are from the first 5,000 variates, and then the y would be n plus I, and the z values would be 2 times n plus I. So let's try that, see what that does. Now you can see that when I pick the numbers off the pile in that order, so all the x values are generated successively and all the y values are generated successively and so on, that I no longer see this strange correlation between the variates. It's only when I pick them out, each triple is an x value is one member from the pseudo-random sequence, the y value is the next value from the pseudo-random sequence, and the z is the following one. In that situation, I will get this behavior. So you can see that whilst these numbers may look random, they still obviously have a relationship to each other because there is a formula connecting them. So I need to be careful of how I use that sequence of numbers. And in short, the thing to think about is that this pseudo-random sequence, because it is uniquely defined, I need to make sure that any correlations in that sequence of numbers does not correlate with the features of the integral that I'm trying to calculate. So in the case of this sphere, if I go back to what I had before, if I just do undo and go back to the previous code, if I run it, you can see that I was using these pseudo-random variates to generate triples, and obviously that caused a very bad correlation when I lay those points out within the sphere that I'm trying to calculate.